Customer segmentation project, XLR group 4. We arrange the imports and functions together. Then we load the data and describe the data. The data types show that there are no data type clashes like strings in integers and integers in string data values, because most of the data are count values, and that is what we expect the data type to be. The values are within ranges, as we can see from min and max values. So the only problem is because of the missing values, which is income. There are 24 missing values. We use median imputation for robustness against outliers, as well as to preserve the data. We impute the value here, duplicate, we visualize the product categories. So these are the categories based on the products bought, like fish, meat, fruit for primary, wine, sweets and secondary. Here we engineer the features. We use the latest enrollment date within the data set to calculate the age, to keep the age calculation within the context of the data set. We also make another feature called number of accepted campaigns, where we add columns accepted CMP 1 to 5 and response. We one-hot encode the variables education and marital status. Then we scale them. We only scale integer columns. We ignore Boolean values. Also, we ignore number of accepted campaigns. We don't scale them because we don't scale the Boolean values because they already are within 0 and 1, therefore don't need scaling. We don't scale number of accepted campaigns because we want to make the clusters more sensitive to the number of accepted campaigns. We identify outliers. We use isolation forest. The main principle behind isolation forest is that a dataset requires fewer number of splits to identify outliers. Here we have 4 hyperparameters. N estimators, it is a number of decision trees we construct to make the splits. The decision trees randomly choose the columns as well as the split values once we choose the columns. The distribution is uniform. The contamination level. So the models, the decision trees, once they split the values, calculate an anomaly score for each row, and when we repeat the process 100 times, we have 100 anomaly scores for each row, and therefore we calculate the average anomaly score. The contamination level determines the minimum anomaly score to consider a data point as an outlier. So if the anomaly score is below the minimum anomaly score of a row is below the minimum anomaly score, we don't consider it as an outlier. We fit the model and we predict the outliers on the data set. The outliers is, so when the outlier prediction is 1, it means that the row is an inlier, and if it's -1, it's an outlier. So we keep all the values whose outlier prediction is equal to 1. In that process, we eliminate 3 outliers, which is 0.13%, which is equal to the contamination value of 0.001, close to that. And this is the post removal data and scale. So here is the PCA dimensional reduction. Since we have 28 columns, the goal of PCA is to help us in this for our case, customer segmentation. The goal of PCA is for us to identify the clusters visually. So because there are 28 features, we can't plot them, and we can't plot 28 dimensional plots. So we try to reduce that and see if we can capture it in fewer dimensions like 2 or 3, as that's what we can see. And based on the scree plot shows how much variance each PCA component can explain. So the PCA component 1 can explain 34.02 and PCA component 10 can explain 2.68. So all the top 10 components together can explain 80% of variance. So we need at least 10 components to plot the data to better visually capture the clusters. So since we require at least 10 components, it's of no use. Because we can only see 2 or 3 dimensional plots. That's why we use TSNE. And in this case, we use PCA reduction, and we use 0.9. So 90% of the variance we want to capture through. So we want to use as many components as required to capture 90% of the variance, and thus we fit the data cleaned to form PCA data, and we form the TSNE reduced data on that. Here is the reduced data. So these are the 4 hyperparameters. N components is the number of TSNE components, random state for reproducibility, perplexity. Perplexity determines like the lower perplexity implies we form lower clusters, smaller clusters, a large number of smaller clusters, and higher perplexity we form a small number of large clusters. We require n iterations. The goal of n iterations. So the TSNE plot, what it actually does is it takes the high dimensional data and pushes the data closer to each other based on the similarity score. So it has 2 components. One is attractive force, another is repulsive force. The attractive force is directly proportional to the similarity between points, and the repulsive force is directly proportional to the dissimilarity between points. And we apply the force 1000 times and thus move the data closer and closer based on the perplexity value. And thus we have this TSNE plot. First we use hierarchical clustering. We use the dendrogram to determine the number of clusters. We use the linkage method WORD. We can have 4 linkage methods: WORD, complete, single, and average. We use WORD because we want to keep within the cluster. We want to make cohesive clusters, and WORD ensures that the clusters we merge together keep increase minimum, like the clusters that form have minimum increase in variance when compared to the clusters from which they have formed. Yeah. So this is the dendrogram. If we can see, these are the distances at which the cluster has formed. So this is the last cluster formed. The distance between the subclusters of this cluster is 1696. As you can see, this is the one cluster, this is another cluster, and the distance between these 2 clusters is 1696, and then another one is 1449. So this one is the cluster. So for these 2 clusters to merge, so the distance between these 2 clusters is 1449, and the distance between these 2 clusters is around 958. We use the cutoff line. We determine the cutoff line based on the maximum jump. So here is how we determine the maximum jump. If we observe, so the last 6 clusters are 1, 2, 3, 4, 5, and 6. So these 6 clusters have formed at 6 different distances. Yeah, the clustering algorithm we use is agglomerative clustering, which treats all the rows as single point clusters and merges the nearest points together. That is how, and at each step it keeps merging the nearest points and forming the clusters. So if we observe, the sixth cluster was formed, and the distance between the subclusters was 327, and the fifth cluster was formed, and the distance between subclusters was 369. I mean the last sixth, the last fifth, the last fourth. If we can see, the jump between the clusters is highest at 490. So this is the maximum jump. So that's why we use this as a heuristic to determine the maximum number of to determine the maximum distance, minimum distance between clusters for them to be a single cluster. So the distance, if the distance is more than this, we consider them as separate clusters. If the distance is less than this, we consider them as one cluster. And if we see that the distance between these two clusters is greater than 958, so we consider them as separate clusters, and so is this. Yeah, because for these two clusters to combine, it at least requires more than, from 400 it has to rise to above 400, so 1057. So the jump is too much, so we don't consider them as, so we consider them as separate clusters. Based on that, we form 4 clusters. Yeah, the number of clusters, agglomerative clustering, and the Ward method. And these are this is the KSNA visualization of the hierarchical clusters formed, and this is the silhouette score and DB score. The difference with silhouette score calculates the average of the silhouette score of each point once the clusters are formed, while DB score, it calculates the similarity between the most similar clusters formed. So DB score focuses on the worst case scenario clusters, but silhouette score focuses on the overall clustering mechanism, overall clustering procedure. We also use k-means. We use elbow method to find the optimum number of clusters, and we also plot the silhouette score for each number of clusters, and we find that the silhouette score is maximum for 4 coincidentally, which need not happen. K-means has only two main hyperparameters, number of clusters and random state. Once we set the number of clusters, the initialization of the initial centroids happens based on the maximum, like we choose 4, because we have 4 clusters, we choose 4 centroids such that those 4 points are most distant from each other, and based on that we assign the points to the nearest centroid and form new clusters, and we repeat the process and calculate the centroids for each new cluster, and once the centroid doesn't change by much, we stop the mechanism. So these are the these are the 4 clusters, and the silhouette score is 0.522, DB score is 673. Here we use DB scan also to find the clusters. The DB scan, in case of DB scan, we have 2 main hyperparameters, epsilon value and minimum number of samples. Epsilon value is the radius of the hypersphere, and the minimum number of samples is the number of data points that must be within the hypersphere of radius epsilon for it to be considered as a core point. So DB scan first finds core points and then border points and then outliers, and based on that, whenever 2 core points are within epsilon value distance, they form a single cluster. So it runs based on the elbow method, if we find that 3 seems to be a good candidate for epsilon, and the common heuristic is that because we have TSNE reduced data, we use only 2 columns, so there are only 2 dimensions. So the heuristic is that we use the minimum number of samples to be equal to 4, and thus we run the scan and find that 1 is the best epsilon and 4 is the best minimum number of samples. We run the scan again by changing the by changing the epsilon value to 1 and find if there is if we can optimize over this and find that the new epsilon value is 0.7 and the minimum number of samples is 5. Thus these are the best parameters, and based on this we form the cluster, and we see that the DB scan has performed very poorly because it has identified a blue and brown cluster which contains of very few points, and it has identified all the other points as noise. And this is the silhouette score when we ignore the noise points, and this is the silhouette score when we include the noise points, and the silhouette score shows that the clusters are overlapping. Now we go to the Gaussian mixture modeling. The main principle behind Gaussian mixture modeling is that all data arises from either a single Gaussian distribution or a mixture of Gaussian distributions. So the n components range, we see that we check how many Gaussian distributions we require to fit the data best, and we see we start from one Gaussian distribution up to 10. So we check if 2 Gaussian distributions will fit the data or 10 Gaussian distributions will fit the data. So these are the hyperparameters, n components. So the number of Gaussian distributions we think might fit the data. Covariance type, it considers the variance of the feature as well as the covariance between the features full. The tolerance, so once the change in the hyperparameter, once the change in the parameters is within 10 power minus 3, we stop the iteration, max number of iterations. So once we initialize the Gaussian parameters, we run the iteration 100 times, where we try to better estimate the centroid, the variance, and the weight of each Gaussian to contribute to the distribution. So we revise those values 100 times based on the expectation maximization algorithm. The initialization parameters based on k-means. So we initialize the centroid based on k-means algorithm. We use AIC criterion. So we try to minimize. We select the Gaussian mixture, the number of components, which based on so we select the number of components that minimize the AIC criterion, because it ensures both the best fit as well as penalizes the model complexity. Here we see that for 10 components, the AIC criterion is the lowest, and so we use 10 components and thus form 10 clusters. And here is the silhouette score and the DB score. We make a data frame out of all the 5. So DB scan mask is where we ignore the noise points, and DB scan where we consider the noise points, and these are the hierarchical clusters, and these are the silhouette and Davis Burdon scores. Now we move on to the supervised learning algorithm. As we can see, our target variable is number of accepted campaigns. We see that 0 dominates, so it is a 0 inflated data, and the prevalence is, so 73% of the rows have 0 as the number of accepted campaigns. So we use 0 inflated regressor. We use the decision tree classifier to identify whether number of accepted campaigns is 0 or greater than 0. And once we identify that it is greater than 0, we use linear regression to predict the number of accepted campaigns. So this train test split, here we fit the model. Now we assess the model accuracy. So these are the values: root mean square, mean squared error, and mean absolute error. And we see that the R squared is very poor, and these are the predictions. So since we use linear regression, the output is a float point, but we actually convert it into integers, into the nearest integer. So if it predicts 3.4, it will be rounded to 3, and it will be, if it is 3.5, it will be rounded to 4, and thus we see the predictions. So when actual is 0, it predicts correctly 271 times, and it predicts it as 1 and 2, and if it's when the actual is 1, it predicts as 0 45 times, and 1 as 21 times, and as 2 as 23, and even predicts as 3. So it seems the performance is pretty poor, as shown by R square and these values. So the macro average is 0.26 and the weighted average is 0.67. So it's pretty, the estimation is not so good. So we also move on to XGBoost. Yeah. In this case, yeah, objective. The objective is the loss function we use. So the loss function is the least squares. So we want to minimize the the squared error. We want to minimize the squared error. So the number of estimators is the number of trees. So XGBoost is a sequential, like we create 100 trees where each subsequent tree tries to optimize its performance on the misclassifications of the earlier tree. The learning rate is the learning rate is the parameter that it improves the convergence towards the, I don't know what this is. Max depth is the number of nodes till it reaches a leaf node. A leaf node is where the node contains only a single row. So that is the maximum depth to which we allow the maximum depth we allow the tree to grow. So it need not be that the last after the maximum depth it has to give rise to, it has to isolate a single row. So even if it doesn't, it will stop at 10. So we train here and we test, and we see that the R square is much better. And here we see the classification. Here also we use the same. We round it to the nearest integer. So in case of 266, when 0 is 266, so actual prediction is 266. When the actual is 0, it predicts as 1 as 41 times. So, but overall it performs better than that. Now we move on to the deployment part. This is a Streamlit app. It shows the data, initial data, and here we can see the general description of the data. Now we can see the products histograms. So this is the main histogram that shows the distribution across of the products across tertiary, secondary, and primary. We move on to feature engineering. So we create four new features, frequency, monetary for RFM analysis, number of accepted campaigns, customer tenure, as well as age on last enrollment date, as I have explained in the modeling part. So this is the RFM analysis, and this is the 3D scatter plot of the RFM, and we see that the blue points are the potential loyalists, red are the at-risk customers, green are champions, and blue and violet are the ones potential who can leave the service. Here also the same methods we have used, outlier detection through isolation forest, and here we have used fewer columns, as we have used recency, frequency, and monetary instead of the catalogs, instead of the actual product categories, and the places like web or store or catalog through which they make the purchase in order to in order to simplify the model. So TSME visualization of the data, same steps we use in our XGBoost we also find the feature importance, and based on these two we actually have our business insights. So these are broad insights where we don't go into much detail. We simply say low frequency, like the suggestions are based on recency, frequency and monetary. So as you can see for K-means, for cluster 1 these are low income, low frequency people, standard offers, and for cluster 4 these are younger people, lower income, also standard offers, because we use age on last enrollment date. In the detailed insights part we go into much detail where we suggest what products to promote, what channel to target, and what type of what helps them, what incentive we offer, which is discounts or deals, and the type of campaign they responded to the best, which is campaign 4 type in case of hierarchical clustering. And if we use K-means, the cluster 0 responded to campaign 4 type. We suggest store and catalog, also web. We promote wines and gold.